For thousands of years, humans have taken objects from nature to create a better world for themselves. Take, for instance, mud bricks from antiquity that were used to build dwellings.
Through trial and error, early carpenters learned that just building structures from plain mud often led to unstable structure. But when they combined mud and straw together, they came up with a new structure that resists both squeezing and tearing, resulting in a much better dwelling. Although they may not have known it, these early builders were using composite materials.
Even though the use of the term composite materials is generally synonymous with space-age materials, composites, they've been around for a long time. Basically, a composite material is formed when you combine two or more items that have very different properties. Many composites are made up of just two materials, one that acts like a glue to surround and bind, and one to reinforce like fibers or fragments. When combined together, these different materials usually work together to make the sum of the parts much better than the original materials alone.
Today, the use of new composite materials can be seen in virtually all space-age designs, from new aircraft used by you and me, the general public, to even next-generation spacecraft for future space missions. Now, this turn to composites is because weight reduction combined with strength has always been a critical goal of flight, even since the beginning.
The first aircraft ever made were built from wood and fabric material, but it was soon realized that a major change needed to be made to increase the strength and durability of aircraft. The change came with the introduction of strong and lightweight metals like aluminum. Since that time, the use of these types of metals have been the state-of-the-art for both aircraft and spacecraft.
Today, metal spacecraft are still state-of-the-art, but researchers have begun to look at new ways to build spacecraft that could offer better alternatives to metal. In fact, NASA is already testing what could be the next big step in spacecraft design. Right here at NASA Langley, it's called the Composite Crew Module, or CCM.
I met up with NESC Principal Engineer Mike Kirsch to find out a little more about this innovative design.
Mike, this CCM to me looks a little familiar. I mean, I'm thinking 60s Apollo capsule.
It's very similar to the Apollo program. Many shapes will work for the mission that this was intended, but in order to kind of streamline the decision process, the Apollo shape was picked. And that way we could leverage the aerodynamic data that we collected during the Apollo program. So this is a slightly larger version of the Apollo. The Apollo was roughly 4.3 meters in diameter, and this one's 5 meters in diameter. If you recall, Apollo had 3 astronauts on the inside. This was designed to carry 6. Later lowered to carry 4, but the volume is still there to carry 6 crew to and from station.
Mike, we've been talking a little bit about composite materials. What type of material is the CCM made of?
This is a carbon graphite epoxy resin system. It's a fabric that was hand laid up on a mail tool. And then you put the entire system into an oven. It's actually a pressurized oven called an autoclave, and it gets cooked and it comes out hard.
Let me just kind of make sure I understand this. Kind of like a wire mannequin wrapping fabric around it. Is that kind of what?
Yeah.
Okay.
Yeah.
Okay.
That's a very good analogy.
Okay.
And then that's only the first step, though. So after that, we add what's called a aluminum honeycomb. You glue the honeycomb to the skin, and you cure that. And then after that, you lay another skin on top of the aluminum honeycomb. And then you put that back in the oven and you cure it. And when it's all done, it comes back as an assembly. So you have a thin skin on the inside and an aluminum honeycomb in the center, and then another thin skin on the outside. And it's rigid and cured just like that.
And you know, as you're describing this to me, I'm thinking, wow, that's a lot of stuff. But this is, I mean, I can barely feel it.
It's very lightweight, which is the idea of composites. It's a high strength and stiffness to weight, which is one of the objectives of the project. The purpose of the project was to get some NASA guys some hands-on experience designing, building, and testing with composites. Now, this is an alternative to the mainline program. The mainline program, which is Constellation, in particular the Orion project, which makes the crew capsule, they chose aluminum lithium, which has very similar strength and stiffness to weight characteristics. But this is an alternative, and by using composites, it enables complex shapes to be made. And to give us a real-world comparison between the aluminum lithium mainline program against composite structure of using the same set of requirements.
Mike, you said earlier that composites allow you to test different complex shapes. Talk to me about the CCM shape. Why this shape?
When the project was kicked off, we tried to respect the interfaces that the Orion project was using for their crew module. Now, Orion at that time had baselined this component called the backbone. And this backbone was really used to help them manage the stuff that goes inside the capsule. What the composite team did is we tied our floor to this backbone shape. Then the next thing we did is we actually shaped the floor to take advantage of the fact that the backbone was there. And what it did is it brought in these lobes, and the shape of the lobe is the shape that the floor would want to take when pressurized. If we didn't have the backbone, we didn't have the lobe floor, then what happens is it would be a dome-like shape. When you pressurize a dome, it wants to go to a ball shape, a sphere. And by tying it to the backbone and putting in the lobe shape, we could reduce the stiffness in the edges, which saved mass. Now, the composites don't inhibit aluminum lithium from having a similar shape. It's just much more difficult to put a lobed shape into an aluminum lithium system.
Mike, what are some of the reasons people use composite materials?
Well, composites are known for their strength and their stiffness for mass. So they're very lightweight materials, and they're used oftentimes in the high-performance industries. Composites are also thermally stable. What that means is that they don't change shape as they change in temperature. Composites are also very tolerant to fatigue. Any application where shape is of critical importance. In the airplane industry, they like it on wings. They want to manage the shape of the wing, the mast of a sailboat, the hull of a sailboat, the racing sailboat, tennis rackets, racquetball rackets. All of those use carbon fiber because they're very, very stiff, very, very lightweight.
Mike, any tests to failure to see if the CCM would completely fail?
Absolutely, and part of the program was to pressurize it until it failed. And we pumped it full of water with that same set of instrumentation on there and continued to pump it up until it actually cracked or popped. Now, we were expecting a fairly dramatic failure. All of our predictions were that it was going to be dramatic, and it turned out it was not very dramatic at all.
And is that positive?
That's a very positive result. Now, this was designed to dock to the International Space Station, so it's designed for an internal pressure of 15 psi, just like we're breathing here on the ground.
Right.
But you actually multiply that by 2, so you have a little bit of margin, some of what we call a factor of safety. So it's actually capable of 31 psi to be where we were comfortable. It actually failed at 53 psi, significantly higher than its design ultimate capability. But that shows that we have a fair amount of damage tolerance still remaining in the design. This project's been extremely successful since its inception, and we're very excited about where it goes from here.
Mike, thank you so much. How exciting. We're standing by to see what happens.
All right.
So far, we've been hearing a lot about how weight is a huge issue when you want to fly something. And of course, the structural integrity and safety of the craft is important as well. Now, in the past, to compensate for safety, vehicles were generally made much heavier than needed. This was due in part to a lack of understanding about certain structural test failures, like buckling. Today, researchers have a much better understanding of the buckling process and the fine balance between weight, safety, and performance in vehicle launch design.
For spacecraft design, researchers are using a technique to test shell buckling that will help them better understand this balance. I spoke with Mark Hilberger here at NASA Langley to find out a little more.
So Mark, why is NASA testing shell buckling?
Well, shell buckling is one of the primary failure modes that we have in launch vehicle structures. And what we're doing today is trying to revise some old design guidelines that NASA generated a long time ago for the Apollo era. And why it is critical is if we are building structures too heavy, like we have in the past, we're not going to be able to get the payload into space like we want to. So we're studying here the fundamental physics of buckling and then trying to apply that to an updated design criteria that will allow us to make us lighter weight, more efficient, safe launch vehicle structures. I've got a little test I can show you. This is a typical beverage can, and we've all crushed these before under our feet, I'm sure. And what we mean by a thin shell is that it has a very thin wall and it's shaped like a cylinder. And if you could picture this as being much bigger and used in a launch vehicle as like a fuel tank or something like that, they're subjected to very high loads. And one of the problems that we're studying is how do these cans buckle so we can design better launch vehicle structures. So I'm just going to turn this screw and apply a load, a compression load on this can, and I'm going to try and make this buckle. Oh.
Pretty immediate.
Yeah, it's pretty immediate and catastrophic.
3, 2.
Launch vehicles are also cylindrical structures like these with thin walls, so they have all the same basic physical response characteristics that a can would have. And so when they're subjected to load, they can also exhibit catastrophic buckling failure. So when they're first trying to develop rockets right after World War II and you see them going up on the launch pad and then they just crumble, that was a buckling problem. The buckling phenomenon itself is when you're applying a compressive load to a structure and it can no longer withstand that load, and so it causes the can's cross-section to crush inward. So it's imperative that we understand the buckling process. That obviously was a very simple example, but what I have behind me here is a smaller laboratory scale test article that we would use to understand some of the basic physical principles of shell buckling and try and apply that to understanding larger structures. So what we have here is a small scale structure. We're studying various aspects of how it buckles, the effects of geometry and different types of load on the buckling behavior. You can see there's all sorts of instrumentation on here, so we're much more scientific than just crushing the can.
In a vice grip, right.
Yeah,
Right.
So we then take that data and use that to compare to our models to see how well we really understand the process.
All right, in addition to the wires and the things I see attached, I see little tiny dots.
Yeah.
What are they there for?
Well, many years ago, NASA started working with some universities to develop what we call a video image correlation system. And what it is it's a series of digital cameras that we position around the circumference of the shell, and it monitors this speckle pattern that we've painted onto the shell. And during the test, as we're loading it, it's monitoring the movement of the shell wall.
The slightest movement will be picked
up. The slightest movements, sub-millimeter movements. And the really nice thing is, what you see here is a laboratory scale. We're down at Marshall also testing full launch vehicle size structures. We use the same technique, we just use bigger dots.
Mark, what's the difference between the testing, the shell buckling testing they did on Apollo, and the shell buckling testing you guys are doing right now?
Oh, that's a great question. I mean, back in the Apollo era, they were just starting to understand sort of the fundamental physics of the buckling process. The best thing that they could do is run a lot of tests, but not really get a handle on the real physics. But they did a great job because they got to the moon.
Right.
What we're doing now, though, is we're applying more rigor to how we run our tests, the types of measurements that we take. We have new measurement technologies, we have new analysis tools that allow us to very accurately predict the behavior of these shells.
It's always increasing technology, huh?
Absolutely. It's hard to keep in front of it.
I know it is. You're doing a great job. Thanks so much.
Thanks.
Because composites are being used more and more in passenger vehicles like cars and planes, NASA researchers are taking a hard look at how they can make them more robust. Now, as they become more robust, they still have to maintain some of the benefits that composite materials have to offer, like weight reduction. Yeah, this is a tough task, but NASA researchers, they're up for the challenge. I caught up with NASA aerospace engineer Don Jegley to find out more about this new design called Perseus that may be a game changer in composites research. Don, how are you?
Hi, how are you?
Good, good to see you.
You too.
Good. So we're here today to talk about composites and Perseus, right?
Right.
Let's start from the top.
Okay, well, Perseus stands for Pultruded Rod Stitched Efficient Unitized Structure.
Okay.
What that means is that we have a large panel, and this is a Perseus panel.
Right.
And if you look real close in here, you can see stitches. It's all held together by stitches. And what you'll notice when you look at this panel, rather than a normal aircraft panel, is you don't see any fasteners. In a normal airplane, you've got rivets all over the place holding every part together. In this case, we have no rivets.
Right.
Everything's held together by stitches.
Okay.
Now, composite materials have been around for a long time. NASA have been working with them for 40 years. Industry's working with them, and they're now getting out into real aircraft structures.
Gotcha.
But what's different about Perseus is a couple things. First of all is the stitching. Composite materials, composite structures are put together using layers of graphite epoxy or carbon epoxy materials that's all built up into whatever configuration you're looking for. With Perseus, what we're trying to do is build very large unitized structures. so we can get away from all those fasteners by putting in the stitches and by making very large parts. So composites are useful. Composites are good because they're lighter weight than aluminum. With lightweight structure, you can cut down on your fuel costs. And of course, one of the things NASA's looking at today is reducing the amount of fuel that's used and producing less pollution. So we're looking at the next fleet of aircraft would be lighter and more fuel efficient.
What are you doing with this piece?
Okay, this panel was fabricated by Boeing. We're going to do the testing here, and what we're going to do with it is we're going to put it in this test machine, so we're going to slide it back.
Right.
We're going to take the platen here, raise it up, put the panel underneath it, and then position the platen so that it's just at the top of the panel.
Okay.
Now, this machine can apply up to 1 million pounds of loading. So what we're going to do is bring the platen down to the surface of the panel and then slowly apply load to push the panel down.
Okay.
While we do that, we're going to monitor the behavior of all the strain gauges here to look at what the panel's feeling, and we're going to have additional measurements. So we're going to look at the displacement, how the panel moves in a couple different directions during the test. So what we're going to try to find out is how the panel behaves while we're pushing down on it, and then we're going to take it to failure. And what's going to happen is we're going to get a failure somewhere in the panel, probably somewhere in this region here.
Okay.
And what's going to happen is we'll see what the failure load is and where it starts, and then we'll take a look at all the instrumentation we have and compare that to our analysis. Because right now we have an analysis of the panel, but the reason that we have to do the testing is we have to make sure our analysis is right. And because composites are a lot newer than aluminum, and particularly Perseus doesn't have that much of a database to draw from, we have to do a lot of testing to make sure we really understand the behavior. You wouldn't want to put this kind of structure on a real airplane unless you can predict its behavior. And that's what NASA's been trying to do with Boeing, is develop the technology to really understand that behavior so we can predict it.
Well, good luck on the test.
Thank you very much.
Definitely, we hope to see this on a future airplane.
So do I.
Right on. Okay, so far we have seen some of the ways that NASA uses composite materials, but NASA's not the only organization to be using them. Nah, there are many industries that use them too, like the auto industry. Whether it's a huge car company or a startup, all of them are looking for ways to combine strength with weight reduction to make their cars more efficient. One company called Edison 2 is taking that weight reduction to the limit. They have developed a car for the very light car category of the 100 miles per gallon X Prize competition that they feel is the most efficient auto platform ever built. This little car is amazing. It takes design cues from some of the top race cars in the world, while also being incredibly safe with phenomenal mileage. I spoke with my buddy Oliver Kutner to find out more about it. So this is the VLC?
Yep, a very light car.
Very light car. Tell us all about it.
Well, we were trying to build the most efficient car. It's designed to be a 2- or 4-seat car, and it gets 111 miles per gallon combined EPA, 129 on the highway, and we did it by basically building the lightest possible car with the lowest aerodynamic drag. The car substitutes pressure drag for friction drag, like an airplane or a rocket would. You know, these race cars are carbon fiber, and you know, this was a race for a lot of money, so we didn't leave any stones unturned. What it really is, it's kind of like space exploration. What we tried to do is to depart from the ordinary and build it very light. And the auto industry has a very difficult time doing it because of all the legacies, the large corporations and the huge amounts of money involved in making a major shift. And this car demonstrates that the shift exists.
Can you tell us some about the materials that you use to build this car?
It's steel, aluminum, and carbon fiber, and just using it wisely where necessary. It's a steel chassis car, but it's a carbon fiber bodied car, and the wheel centers are carbon in this case.
Do you have any examples or something you can show us?
Here's an example. The wheel is unsprung weight and it's rotating mass. So we actually have the center of the wheel out of carbon.
Okay.
And the outer part is a cast magnesium piece and the inner part is a machined aluminum piece. Altogether, I think this is a 6-pound or 7-pound wheel. And you know, it's an example of using more difficult and more costly materials where their payback is greatest. And in this case, it was worth it, we felt, so that's why we did it. A car is a series of compromises, and you know, you have to also balance cost in all of this. So while we all want a super hot rod that's all carbon fiber, which might be the best solution, it may not be the most realistic if you want to sell 1 million copies. So you put your trump card material where it makes the biggest difference.
So Oliver, tell us how you got the idea for this car.
It was the X Prize. I mean, the X Prize said, you know, you can win $10 million if you build the most efficient car. And then I went to my good friend Ron Mattis, who's a longtime American Le Mans Series and Le Mans race car designer engineer. And he basically reeled me down to reality. There's no substitute for efficiency in the platform, and that's what this is.
Can you tell us how it works?
Well, in this case, we have a gasoline-powered engine. It runs on E85, and but this car can be run on any fuel source. It could be a diesel car, it could be a gasoline-only car, it could be a hybrid and electric. The efficiency comes out of the design of the car itself. That's what does it.
Is it powerful?
It's quite powerful.
Yeah.
It doesn't have that much horsepower, but it's quite quick and it handles extremely well. The NASA programs have been really crucial to a lot of material science and how we do things, and in certain industries they've changed the way things are done. But in automobiles, we've kind of missed the mark, and in many ways we're still building the same 4,000-pound car to move the 200-pound person. If we embrace this as a method of how to build cars, regardless if they're electric, hybrid, diesel, gasoline, the United States of America could become an oil exporting nation. Just embracing the principle of this, the efficiency would be a leap from what is today.
Oliver, thank you so much. You know, I look forward to driving one of these VLCs. You know,
Thank you.
Maybe a basic black.
Next time you come, we'll have one for you.
Please, make sure,
All right.
make sure it's all glossed up for me. Hey, good luck with everything.
It's good.
Take care.
you.
Thanks, man.
As you can see, composites have really changed our world.
That's right. And with NASA on the case, composites will continue to improve for years to come. That's all for now. I'm Johnny Alonso.
I'm Jennifer Pulley. We'll catch you next time on NASA 360.
Made were built from wood and fabric material, but it was soon realized that a major change needed to be made to increase the strength and durability of aircraft. The change came with the introduction of strong and lightweight metals like aluminum. Since that time, the use of these types of metals have been the state-of-the-art for both aircraft and spacecraft.
Today, metal spacecraft are still state-of-the-art, but researchers have begun to look at new ways to build spacecraft that could offer better alternatives to metal. In fact, NASA is already testing what could be the next big step in spacecraft design. Right here at NASA Langley, it's called the Composite Crew Module, or CCM.
I met up with NESC Principal Engineer Mike Kirsch to find out a little more about this innovative design.
Mike, this
That was hand laid up on a male tool. And then you put the entire system into an oven. It's actually a pressurized oven called an autoclave. And it gets cooked and it comes out hard.
let me just kind of make sure I understand this. Kind of like a wire mannequin wrapping fabric around it. Is that kind of what?
Yeah.
Okay.
Yeah.
Okay.
So that's a very good analogy.
Okay.
And then that's only the first step, though. So after that, we add what's called a aluminum honeycomb. You glue the honeycomb to the skin, and you cure that. And then after that, you lay another skin on top of the aluminum honeycomb. And then you put that back in the oven and you cure it. And when it's all done, it comes back as an assembly. So you have a thin skin on the inside and an aluminum honeycomb.
Space age materials, composites, they've been around for a long time. Basically, a composite material is formed when you combine two or more items that have very different properties. Many composites are made up of just two materials. One that acts like a glue to surround and bind, and one to reinforce like fibers or fragments. When combined together, these different materials usually work together to make the sum of the parts much better than the original materials alone.
Today, the use of new composite materials can be seen in virtually all space-age designs, from new aircraft used by you and me, the general public, to even next-generation spacecraft for future space missions. Now, this turn to composites is because weight reduction combined with strength has always been a critical goal of flight, even since the beginning.
The first aircraft ever
For thousands of years, humans have taken objects from nature to create a better world for themselves. Take, for instance, mud bricks from antiquity that were used to build dwellings.
Through trial and error, early carpenters learned that just building structures from plain mud often led to unstable structure. But when they combined mud and straw together, they came up with a new structure that resists both squeezing and tearing, resulting in a much better dwelling. Although they may not have known it, these early builders were using composite materials.
Even though the use of the term composite materials is generally synonymous with space,
CCM, to me, looks a little familiar. I mean, I'm thinking 60s Apollo capsule.
It's very similar to the Apollo program. Many shapes will work for the mission that this was intended, but in order to kind of streamline the decision process, the Apollo shape was picked. And that way we could leverage the aerodynamic data that we collected during the Apollo program. So this is a slightly larger version of the Apollo. The Apollo was roughly 4.3 meters in diameter, and this one's 5 meters in diameter. If you recall, Apollo had 3 astronauts on the inside. This was designed to carry 6. Later lowered to carry 4, but the volume is still there to carry 6 crew to and from station.
Mike, we've been talking a little bit about composite materials. What type of material is the CCM made of?
This is a carbon graphite epoxy resin system. It's a fabric